My name is Steven Reiner. I'm with the Alan Alda Center for Communicating Science at Stony Brook University. This is a special edition of Science on Tap, without the tap, but with plenty of science. It's also taking place here at Stony Brook on Earthstock Week, which is all about the Earth and what we can do to save it and protect it. And to that end, our guest today is Dr. John Warner, who is the preeminent green chemist in the United States right now. Let's start with a basic question. What is green chemistry?
Well, green chemistry is essentially the science of how to make things safely. I think that would be a fundamental, but if you imagine, we hear about red dyes that cause cancer, we hear about plasticizers that cause birth defects and monomers that cause endocrine disruption, and any sane person should say, why in the world would a chemist make a toxic material? Why wouldn't they just make safe materials?
Well, why in the world would a chemist make a toxic material?
Well, they don't want to. The problem is that if you look at the curriculum that a chemist takes to become a chemist, you look at the undergraduate and the graduate classes and training that they take, for some strange reason, we've evolved in our society to have none of that knowledge as part of the training of the chemist. So a person who is given the skills to make a molecule that has never existed before in the world, assembling atoms in unique geometries that have never happened, have no clue whether or not what they're about to make is the most potential carcinogen or neurotoxin in history, because for some strange reason it's just not part of becoming a chemist. So green chemistry is that body of knowledge that I wish to insert into the training of a chemist so that they don't make red dyes that cause cancer and plasticizers that cause birth defects and monomers that are endocrine disruptors.
So this is really a fundamental question of education,
Yes.
of education for a new generation of chemists. But there's also something, if I understand some of the things that you talk about, about how scientists see themselves in the world, what their purpose is, and what their relationship is with their work. Can you talk about that a bit?
We have an interesting dichotomy between the arts and the sciences. And
We think they're quite separate.
And I don't even know what that means. Was Galileo an artist or a scientist? Was Da Vinci an artist or a scientist? When did we invent these words? Well, when we invented the university and the requirement to put people in departments and compartmentalize, and it is that very dissection of human behavior that's at the cause. And I think arts have it well. Okay, an artist can look at a painting and critique it very technically, look at the use of the brush stroke, look at the use of color, and very technically analyze that piece. But then they can step back and say, it's beautiful, I like it. There's an aesthetic response. In science, we are trained to reject the aesthetic and only focus on the technical. Even the language that we use. I don't say, I made this molecule. When I publish a journal article, I must say 5 grams of this and 7 grams of this were combined. Our whole language is to remove ourselves. So when someone comes and says, hey, that stuff is a carcinogen, I didn't make a carcinogen, 5 grams of this and 7 grams. And that removal of self from the product of science has in part created this dissociation. And I think that's part of the problem. If the field of science can learn a little bit more from the arts and return the self to the process, they would look at toxic materials, they would look at pollution and say, that is ugly, I don't like it.
Is that also a question of personal responsibility, though, ultimately?
See, the thing is it's not really an indictment on personal responsibility. This isn't an epic battle of good and evil. I don't see this as somehow indicting people. When I became a chemist, I asked the faculty members, is chemistry dangerous? If I choose chemistry as a career, will I be putting myself and my future family at risk? And with no malice intended, the response was, if you're asking yourself that question, you should probably get another major, because it was assumed as a fait accompli, chemistry has to be toxic. That's what chemistry is. But we'll wear gloves to protect our skin, we'll wear masks to protect our lungs, we'll wear goggles to protect our eyes, we'll put scrubbers and smokestacks to protect the air, the land, and the sea. So we're good people. We recognize it's toxic, but we'll mitigate the exposure of those toxics using engineering. And that's the way it has always been.
And it doesn't have to be thus.
It can't be that, because every time you hear of a disaster, I promise you, those mitigation policies and technologies were in place, they just failed. So green chemistry says, instead of being dependent on some mitigation of exposure, look at the structure and create a material that has all the properties you want, in addition, have it be non-toxic and environmentally benign.
When you look at nature,
Yep.
and you look at the lab,
Yeah.
what is the difference between the two places in terms of how things are done, and again, on that molecular level?
Okay, and then so first, as a disclaimer, I have no presumption that I have some gifted insight here. I've lived my life, I see the world the way I see the world, and I want to share it with people, but no way do my ego say that I must be right. My observation has been the following. When humans manufacture materials, we heat things up to high temperature, we put things under high pressure, we use all these harsh reagents. If you look out in nature, in leaves and cells and organisms, you find the complexity and diversity of molecular structure that is formed completely, stunningly overshadows what humans can do. But more importantly, the way nature makes those materials. It's all done at room temperature, it's all done at ambient pressure using water as a solvent. So I looked at that, I said, why? Why is there a difference? And what I feel the big difference is that when you learn chemistry, okay, you take all these classes on molecular geometry and atomic geometries, and we learn that electrons around an atom are in a certain geometry. And so when molecules bang into each other to react, 99.999% of the time, nothing happens. They just bang off of each other. And rarely, very rarely, does that perfect geometry happen that the chemical reaction occurs. So what do we humans do when we manufacture things? We heat things up, put things under pressure, just to make the molecules move faster, to increase the statistical chance that maybe the right reaction happens. I feel that that never occurs in nature. In nature, there is never a reactive collision. In nature, two molecules first snuggle up next to each other. And the very same atomic forces that are going to control their reaction control their orientation. So they assemble, they collaborate, and then they react.
So the trick is to get molecules to snuggle in the lab.
Yes.
So how do you do that?
So, okay, the way that you do that is you look at the molecular topography of the electronic distribution around the atoms, and you find electropositive. There is a very technical way that one can do that. My field of science is called non-covalent derivatization.
Non-covalent derivatization.
Exactly, and I'm such a nerd, the license plate of my car is NCD, so I can really go on about non-covalent derivatization. Okay, it's just
But that is the scientific chemical key to some of it. So is it possible to explain that to us?
Okay, so the one way of looking at it is the following. Say you have a group of people, and they're working for a company, or they're a group of people trying to do something, and someone decides to do a personality analysis, a Myers-Briggs or something like that. We find that person A is very quantitative, not so good at writing. Person B is really good at writing, not so quantitative. An unwise organization says, oh, let's send them to workshops and train them to do the things that they don't do well. Last thing you want to do, the reason someone does something well is because they love it. The reason someone doesn't do something well is because they don't love it. Why in the world force someone to be sad and unhappy doing what they don't do? Collaborate. An organization should put people together, match their skills, so that they can collaborate and help each other's weaknesses. What we've done forever in chemistry is we've synthesized that magic molecule. We want it to be red. We want it to be soluble. We want it to have this redox potential. We want it to do this. And you have this massive island of Dr. Moreau molecule that does so many different things. Why not instead do what nature does? takes 2 molecules or 3 molecules and has them collaborate so that different properties are imparted from different molecules. Now they self-assemble together at ambient temperature, and you don't have to do all this excruciatingly painful chemistry in the manufacturing process.
Could you give us a couple of examples from the real world, real products, real uses that demonstrate this?
Okay, so one example, my heart is a pitter-patter right now. In Australia, there is an ALS drug that we designed that's in clinical trials.
This is Lou Gehrig's disease in colloquial English.
Yes, yeah. And there was a molecule that was used in laboratory animals that showed quite promise. But this molecule was completely insoluble. Okay, so it's like brick dust. And so what biologists would do is dissolve it in a nasty solvent, do stuff to it, and showed that in laboratory animals it cured ALS. But we can't get it in humans because all that nasty chemistry is going to be counterproductive. And so we use this concept of non-covalent derivatization to form a material that complexed with that active material to make it now orally bioavailable, now in manufacturable.
Pop it in your mouth.
Yep, and that is one example in the pharmaceutical sciences of how to do that.
What about hair dye?
Oh, hair dye. That is, again, one of the things I like to joke about, and it's kind of silly, and I apologize for being silly, is I feel we chemists have too strong of an ego. Our language is filled with, we're going to make molecules do what we want them to do. We're going to break this bond. We're going to force this bond. You know, when my watch came off of the assembly line, you could almost hear the inaudible screams of all the atoms that we forced in the molecules to do what they didn't want to do, so that immediately this watch wants to go back to where it was before. It wants to fade. It wants to crack. It wants to do everything that we don't want it to do. So I joke and say we should play the role of the molecular psychologist. If we put a molecule or a material on a couch and go, what would you like to do? If it looks up at us and says, I want to be a paint, that's going to be a heck of a pain. It's not going to fade. It's not going to go. Takes the ego out of it. But I'm discovering how molecules are. So I was looking one day. It was really kind of crazy, and I can't explain it. But I was contemplating this process called insect sclerotization. That's a tongue twister for me. And what it is when a bug starts to grow, its exoskeleton can't grow with it. So it breaks off and sheds, and it's soft and white. Over the course of a couple hours, it turns hard and black. Ooh, there's a process in nature that goes from white to dark very quickly under ambient conditions. People color their hair. There's a men's product, I won't name it, but the active ingredient is lead tetraacetate. Think about that. In the United States, you can't sell a house with lead paint, but you can go to CVS and buy this stuff and pour it on your head. Absolutely insane. So I said, and women's dyes are also pretty toxic. So I said, could this process be used for coloring hair? So I looked at it, it's a tyrosinase cascade. I developed a mimicking chemistry for it, called a vendor, got a bunch of gray hair, put it in a beaker, took it out, and it worked. But the problem was that it had black hair and brown hair and light brown hair, and it was all different colors, so I was sad. And I said, oh, well, no one's going to want this harlequin of hair. So I called the vendor, and they said, oh, John, it's not one person's hair. It's a bunch of people's hair. I go, oh, my God. So then I was the grayest person at the Institute. I sit in the chair, I go, hit me. And they put it on my hair, and next thing you know, my hair is exactly the color it was 30 years ago. We have person with dark black hair that's gone gray, took the exact same material, put it on their hair, they got dark black hair. Someone with light brown hair, they put it on their hair, they have light brown hair.
Have you brought free samples for the Stony Brook faculty by any chance? Because it'd be very popular.
Well, actually, if you get on the website of myhairprint.com for $39.99, you can, no, it's actually, we commercialized it a year ago. It's called Hairprint, all right, and it restores your hair to the original color. It is non-toxic. I don't recommend eating it, but people have demonstrated the principle by eating it. And it's permanent, it doesn't fade. But the point here is that it's looking at your hair and coming up with molecules that are doing what the hair wants the molecules to do instead of forcing it. You wouldn't believe the violent chemistry going on when we color hair. But this hairprint technology started from the concept of what would molecules want to do under this environment and allow the hair to drive the coloration. That's why it goes into whatever color, because we're not making the color. The hair is gently making the color.
Now, the example I asked to discuss sounds extremely mundane, very basic, doesn't sound world-changing, hair dye. But indeed, when you multiply this and multiply this by all the mundane things we see around us, the sidewalk, the storefront, the sign, the bottle we drink water out of, cumulatively, you believe that this is really a potentially world-changing, life-changing approach to chemistry. That's the way we live.
There's a lot of complexity in the question that you asked. At the end of the day, I feel the biggest enemy to sustainability is are people waking up in the morning saying, this is too big of an issue for me to contribute to. I'm just one little person that has no impact in this crazy world of nasty that we're hearing about, whatever. And if you can buy a hair coloring product, if you can buy a toothpaste, if you can choose what kind of cup to use and contribute to the successful evolution of a sustainable world and a sustainable society, until every individual looking at themselves in the mirror say to themselves, I can make a difference, we're dead. And so it is the little things that actually matter more, because that's where we all live, is in this space of things that we do every day. And if those aren't sustainable, if we don't care about them, you know, anyone can sit around with big talking heads talking about global climate change and stuff like that, and that is really important. We've got to focus on what we as individuals can do just as much.
You were mentioning, I saw in a talk that you had developed something that was connected with Alzheimer's that was going into clinical trials. So even when we're dealing with medicine and neurological issues, there's an application. Could you explain that a little bit?
Well, the interesting thing about pharmaceutical sciences is one of the biggest concerns that I have is pharmaceuticals in the environment. What we're finding is the FDA requires that a drug be immortal. You know, if it shows that it in the pill or in the IV bag it's going to decompose, you can never get approval to have that product. But when we prescribe drugs to the human population, there is no such thing as the average person. We're all very different. So most drugs are significantly overprescribed. And so person is getting a dosage where maybe 10% does something and 90% we just excrete out and go down the toilet. Now that is starting to accumulate, getting into the waterways, and so now if you were to take drinking water from any municipality and analyze it, you will find oral contraceptives, you will find pharmaceuticals that have biological activity that are really low concentration, and they're flying under the radar screen, but as time goes on, this is becoming more and more of a problem. So green chemistry, yes, we want to cure diseases, we want to do that, but we need to stop making things that are targeted and more specific so that they don't have these negative environmental impacts.
And working with this Alzheimer's drug was one of them.
And the Alzheimer's is another one of our things. It's not quite in clinical trials yet, but it almost is, and that one's really exciting. Yeah, that we have that one too.
Looking at the implications of what chemists looking at the implications of the downstream effect of what they do is really what one of the big problems is. They don't.
Absolutely.
And this comes back to education. This comes back to how we view chemistry. Chemists are usually not very popular people at the cocktail parties or at the buffet line, are they?
Well, I've learned, this scene plays out. We're at some family gathering or some party or something, and someone says, hey, what do you do? And I say, I'm a chemist. It's almost like you can hear the proverbial record scratch, the silence, and the room comes quiet. Oh, and then people murmur, oh, I hated chemistry in high school. And so now I have learned. Ask me what I do.
What do you do?
I'm a molecular architect.
You build things with molecules.
How interesting.
What kind of things do you build?
I don't call myself a chemist.
What kind of things do you build?
Pharmaceuticals to cure people, agricultural agents to feed the hungry, textiles to shelter people in the bad environments, Everything that we interact with is a molecule. Anything that has substance, it drives me crazy. There are products on the market that say chemical-free. Think about that for a second. If you have a product that says chemical-free, what's in there? An idea? You better get your money back if you're paying for an idea. You know, so this concept of chemical-free, so everything in the human-built world and in the natural world is constructed by molecular building blocks. Everything is chemistry, and everything is the product of elegant architecture. It's how the molecules orient together and form structures and reactivity. It's all in the molecules.
You're going to be spending time here at Stony Brook, and you're going to be meeting with, talking to the chemistry department.
Looking forward to that.
What are you going to say to the chemistry department? What are you going to say to the graduate students in chemistry, to the undergraduate students who want to become industrial professional chemists?
So the way I look at it, there's hundreds and hundreds of universities in the United States that have chemistry programs. The amount of green chemistry, or I don't even care what you call it, toxicology, environmental mechanisms, varies from university to university. Stony Brook is definitely on the map. They have hosted green chemistry teacher workshop trainings with an organization called Beyond Benign, where they've had K through 12 teachers come in to integrate into the curriculum.
This is your organization, Beyond Benign.
Beyond Benign, yeah. So Stony Brook is doing a lot, but my ultimate dream is to see the required curriculum change so that someday no chemist graduates from any university in the United States with a degree in chemistry not having had some training in toxicology, environmental mechanisms, or law and policy. That's the dream. And so I hope that when I leave here, we've had a discussion of the commitment of the chemistry department here to integrate that. It's not as easy as it sounds. People say, well, why don't they do that? Well, if no one's ever had these classes, who's going to teach them? If there's no textbooks, what are you going to? So what the Beyond Benign has done is created this program called the Green Chemistry Commitment, where it's asking chemistry departments to join a group of people, and if one department wants to have a standalone class, if another department wants to integrate it into freshman chemistry, and if another one wants to integrate it into organic, if they all share best practices, we can move the ball forward. So I'm hoping and praying that Stony Brook signs the Green Chemistry Commitment and joins UC Berkeley, UC Davis, University of Minnesota, and about 35 other schools that have started this momentum.
I want to go back to the question you just alluded to. How come this hasn't been done? And I know one answer is, well, no one's being taught it. There is no textbook. It just hasn't become part of the canon. But we've come to believe that doing anything that's environmentally friendly, that saves resources, is just unaffordable. We hear it kills jobs. It's not good for industry. It's just too expensive. And you argue that really just the reverse.
Well, I guess what I would say is, how many products, take the word sustainability out. We live in a world of products. When a product fails in the market, why does it fail? It doesn't work, it's too expensive. For us to have a sustainable future, that still has to abide. If we're dependent on regulations or artificial incentives to force people to buy products that don't work, that are too expensive just because they're sustainable, that's a short-term Band-Aid, but the change of an election, that could collapse. So the job is to have the chemists go back in the lab and invent technologies that are significantly better in performance, that are significantly better in cost, and oh, by the way, they're more sustainable too. That is the exact point. If technology, and we have history is filled with technologies that made claims of being more sustainable, and they really didn't work, and they were too expensive, and they probably weren't even really sustainable, and that fails in marketing and charlatanism and very bad things, and we have been tainted and burnt by that. Green chemistry says never depend on guilt to drive a thing. People should want to buy a green chemistry technology absent of the sustainability perspective of it. And so if you accept that definition, I would argue there is no barrier to success in the marketplace. The only barrier is its invention in the first place. And if no colleges and universities have classes in toxicology and environmental mechanisms, who's going to invent them? So the big barrier is invention. So it's all about innovation and creativity.
And then the marketplace will follow.
Marketplace, there's no way the marketplace won't follow if it has superior performance and cost. And it's interesting, like back in 1996, my friends and I, we started the Presidential Green Chemistry Challenge. It's the only award given by the President of the United States with the word chemistry in it. And every year for 20 years, it started in the Clinton administration, survived into the Bush administration, and now into the Obama administration. 20 years, 5 companies get this award for a technology. So you can go back 20 years and get over 100 case studies of companies that have taken a technology, made them more sustainable, made them more cost effective. This is not something that's invisible. It's out there, but here's the problem. If you're a company and your product was toxic yesterday and you've invented something better, are you going to go on TV and tell people, hey, what I sold you yesterday was toxic? So this is happening all the time, but it's a class action lawyer's dream come true for a company to tell people that they've made something less toxic. And so the looking for evidence of it might not be the right way to go about it.
Final question before we open it up to questions from the people here. Stepping back from chemistry and green chemistry for a second and just talking about science and the public and this moment in history that we are in, which is an anti-science moment, it seems. What is the responsibility of every scientist, no matter what discipline, at this particular time in your view?
Okay, so when I was a professor at UMass for 11 years. I had a massive research program. I had 30 to 35 people working in my lab, visiting professors, postdocs, graduate students, undergraduate students, and I had an inviolable law. Anyone working in my lab had to twice a month go to a 3rd grade class, go to a 7th grade class, and explain their research. I had no grants, I had no funding, I just did it because that's what you should do. And those students benefited from it, but the scientists benefited because if you can't explain what you're doing to a 3rd grader, you probably don't get it yourself. And so there's just so much, and that isn't happening enough. People are waiting to get a grant program to. If we in the sciences just did the right thing and didn't hide behind, well, I'm looking for a grant to do the right thing. Okay, so you're going to do the wrong thing until you get a grant? What the heck? And so if we built into the sciences this sense of outreach, this sense of responsibility to communicate, the science departments across the country are all funded by government grants. No one gets a degree in chemistry, physics, paying tuition. They're being sponsored by government grants. They're getting a stipend. We owe it to society to do a heck of a lot better job communicating.
Well, you do a great job communicating, so I want to thank you, and I want to open it up to questions. Yes, can you, I suppose your name and then?
My name is Mariama. I just wanted to ask you, what got you interested in green chemistry?
Oh, it's interesting. You wouldn't really call me a greenie growing up. I wasn't, I think I had a certain sense of responsibility. But there's 2 things that happened, okay? The first thing that happened is I worked at Polaroid and I invented a technology, non-covalent derivatization kind of thing. And as you can imagine, the EPA had no idea what I was talking about. And in the United States, to go to large-scale manufacturing, you need to get approval from the EPA. So as I was down at the EPA, I encountered a friend of mine that I'd grown up with. His name was Paul Anastas. We're from the same city. He's working for the EPA. I'm an industrial chemist. And we kind of said, gee whiz, isn't it funny that the EPA regulates what not to do? Shouldn't they be promoting what we should do? Wouldn't that be more efficient? And so, okay, what is it that we should do? Should we make things less toxic? Yeah. Should we make things use less energy? Yeah. Should we make them biodegradable? Yeah. All of a sudden we get this whole paragraph of what we should do. We better call it something. Let's call it green chemistry. And so that was the beginning of green chemistry and what got me into it. Interestingly enough, it was less of tree-hugging save the world. I consider myself a tree-hugging environmentalist. I mean, it makes big of it. But when I started at this, it was really about practical efficiency, time to market, and things like that.
Yes.
My name is Jay. You mentioned that you have a company beyond Benign. Can you tell us some of your achievements with that or some projects you're working on?
So there's two companies, okay? There's the Warner Babcock Institute for Green Chemistry. That is a for-profit beakers and flask, 42,000 square foot research facility with 30 brilliant, beautiful scientists, and we just invent stuff. We work with companies to help them invent, and then we do our own things. And so we have pharmaceuticals, we have an ALS drug, a cancer drug, an Alzheimer's drug we're working on. We have the hair color technology. We have asphalt paving technology to allow you to use recycled asphalt. We have a wood composite technology that's formaldehyde free. It's just crazy. We're just all over the place having fun. And then there's Beyond Benign, which is a K through 12 university education and outreach. And so two different divisions, one, well, technically three, one for public outreach, one for K through 12, and one for university. So the green chemistry commitment is part of the university outreach. We're kind of busy. Yeah.
Yes.
Hi, my name is Daniel. From a sustainability standpoint, taking a look at like energy industry, in particular the oxygenates added to fuel in the Northeast and other parts of the country, what is the potential to replace or synthesize some sort of other fuel to replace corn ethanol?
Technically, easy. Politically, impossible. And I think that that's the heart of the problem. I think as a scientist, do we need ethanol? Of course not. There are all kinds of different things. But there are so many subsidies and intertwined financial implications of the corn and ethanol economy that's the problem. And that just makes it problem. And that's what's so hard about being an inventor. Because people think that all an inventor needs to do is go in the lab and invent something. Problem is that it's a lot more than that. It has to be something that can be scaled and manufactured. So I can, take, really expensive reagents that are crazy and demonstrate and publish hundreds of articles in journals, but no one actually expects it to be scaled up. That's not going to help the world. And the other thing is, so it has to be readily accessible, it has to be inexpensive, it has to really work. And the problem is the disincentive of the massive forces protecting the subsidies of the ethanol economy. And so who is going to go and tackle that, where you could have brilliant Nobel Prize winning chemistry and no one's still going to do it because of the infrastructure that's preventing it? It's the problem. So a chemist needs to understand those things. I don't believe it's not solvable. I believe there's a path in the future to deal with this. But a lot of people have to work together to make it happen. Yeah.
Okay. Any other questions? Yes.
So you mentioned earlier that so many things nature does at room temperature often look very enticing. And can you mention any particular processes that happen in nature and biological systems that you've been able to co-opt to take the place of a high temperature process that produces vats of crap that
Yeah, okay, so there's a lot of them. So one of the things that I did, it's interesting. I had this disease, this version of psoriasis called Van Besenbesch syndrome, pustular psoriasis. It only happens in the palms of my hands and the soles of my feet. And every 2 or 3 years, I'd be a bloody mess. I couldn't walk, I couldn't hold something. It would last for about a month and go away for a couple of years, and last for a couple of months and go away for a couple of years. Well, while I was at Polaroid, I had a flare-up. Now, spontaneously bleeding all over your lab is a career-limiting experience, okay? Now, Polaroid labs were in Cambridge near MIT and Mass General. I saw an experimental therapy called PUVA phototherapy, where they took a wavelength of UV light, and I put my hands and my feet in a little box, an hour a day, 3 days a week for 9 months, and I'm cured. Looking at that, I said, what's going on? And it turns out that the UV light was hitting thymine in DNA to make thymine and DNA do a photochemical reaction. It's kind of tied to the mechanism of skin cancer. What happens when sunlight hits DNA, the same reaction. Sadly, that's a super efficient reaction in nature. So I said, okay, what if? And so I got some thymine, I started to take some biodegradable polymers, I covalently put the thymine into the polymer, hit it with light, it did the same reaction. So I could make a water-soluble polymer, coat a surface, hit it with light, wash it off wherever I hit it with light would be insoluble, called a photoresist. So using DNA photochemistry of thymine, developed a whole line of photoresist technologies for the electronics industry, actually a hair curling technology, of fingernail polish that's based fundamentally on that mechanism and nature of thymine photodimerization. That's one example. Yeah.
Thank you. Fascinating,
welcome.
fascinating,
Thank you to
fascinating.
have me here.
And we're delighted you're here
Yeah.
at Stony Brook.
Yeah.
Please thank Dr. Warner.
Yeah.
for a wonderful- And that's it for this special edition, Earth Stock edition of Science on Tap. We'll see you soon.